Well, you just have to come further down if it's too quiet, right? But now I think it's louder, no? Okay. So we started from the full Einstein equation, we linearized it, right? We obtained this wave equation here, which is just the usual wave equation, the box operator, with on the right-hand side the source term, the energy momentum tensor. And the object that we had here, right, was the gravitational wave in Lorentz gauge, and where we had subtracted out the trace. And from there, we looked at two different frames, right? We looked at the TT frame and the proper detector frame. So the TT frame, right, recall kind of the advantages that the gravitational wave takes a very simple form, right? We had the explicit form on the board. We saw also in the TT gauge, if we actually look at two free-falling test masses, right, and we take them initially at rest, and we ask, what is the acceleration, right? We found that to be 0, meaning that two free-falling test masses in the TT frame stay at rest forever, right? So we can use this to set the coordinates in the TT frame. So the coordinates are marked by freely falling test masses. And that's the physical interpretation of what is happening in this frame. Of course, there's still physical effects of the gravitational wave, right? So for example, if you look at the proper distance between two test masses, you will get a power of the metric, right? And you will see that despite that the coordinate distance in the TT frame is always constant, the proper distance between 2 points does depend on the gravitational wave, right? So of course you do also in that frame see all the same physical effects of the gravitational wave. Then we looked at the proper detector frame, which is basically the frame that somebody in a lab would naturally use. So there you say, okay, you at one point in space, which you define as your origin, you kind of can always choose space to be locally flat. You expand around this one point in space, right? So there's one point where you can take the Christoffel symbol to be 0. And we saw that in this frame, the separation between two test masses, right, changes according to the gravitational wave. Wait, there's a double dot here, right? Proportional to the second derivative of the gravitational wave in the distance itself. So that's just a Newtonian force acting on the test masses, and that's where kind of the picture of this plus and the cross polarization comes from, because you really see the motion of the test particles. Last time there was also the question, what are these dots, right? Are they cosmic time or are they proper time? So the point is that in the proper detector frame, the difference between cosmic time and proper time only enters at order h squared. So despite that we derived it in actually proper time, right? Then to the order in h, the linear order in h that we're working in, it's the same, and hence for practical purpose we work in cosmic time here. Okay, before we move on, are there any follow-up questions for yesterday? Good. Okay, so today we want to get to the point where we talk about emission of gravitational waves, sources of gravitational waves, power emitted by gravitational waves. But before we do that, we first need to even define what we mean with the energy momentum tensor, or the energy emitted by gravitational waves. So you may think that this is trivial, right? Because you think, well, wait a minute. I mean, a gravitational wave, it's just radiation, like a photon with slightly more complicated polarizations. I know how to define energy for a photon, right? Why is it complicated for a gravitational wave? And it's not complicated if you're in the scenario that we were in yesterday. So if you're in perfectly flat background space-time. Okay, but life is not like that, right? I mean, we live in a universe which is not perfectly homogeneous, right? There's stuff. If you're at LIGO, you make a measurement, right? It's not perfectly flat space-time, right? You have the Earth, you have the gravitational field of everything that's surrounding you, and it's not perfectly flat. So the realistic situation is that actually you have some background space-time, right? Which is does something on some scale L background, and you have a gravitational wave, which is also varying over this background, and both the background and the gravitational wave are time and space dependent. Okay, so then the question is, what even is a gravitational wave? What is the difference between what I call a gravitational wave and what I just call curved background metric? Okay, so the question is, maybe we should have asked it yesterday, right? But actually, what is a gravitational wave in curved background? And in order to even define that sensibly, we need a separation of scales. So the typical picture that we have is, for example, that we have the background metric, which is slowly varying, right? I mean, I don't know, there's a galaxy, a planet, something in the universe. And you have a gravitational wave, which is a much shorter wavelength. So it's kind of really rapidly oscillating, right? So this is some scale lambda gravitational wave. And then you say, okay, well, I'm going to define myself some auxiliary length scale, d, and everything that averages away, when I average over the length scale d, I call it gravitational wave. And everything that is basically invariant, when I average over this length scale d, is what I call the background. So I've drawn it here in terms of length scales, right? It can also be time scales. So at LIGO, right, I mean, the gravitational waves that we're looking for are a wavelength of hundreds of kilometers, say. The gravitational potential of the Earth is not constant on the scale of 100 kilometers, right? I mean, you have just the fact that the Earth itself is there, that the Earth is also not a perfect sphere, that there's gravity waves, right, propagating in the crust of the Earth, like seismic waves, right? All this is on the scale of 100 kilometers. So you could not do this in space for LIGO, right? Because you could not distinguish a gravitational wave from just the usual background of stuff that is happening. However, in LIGO, we're looking for gravitational waves with a frequency of 100 hertz. And all these variation of, you know, the Earth, the seismic waves in the Earth, all these things are lower, right? They're at lower frequencies. Like also, I mean, all the facts from kind of the moon rotating around the Earth rotating around the sun, right? The LIGO even being on the surface of the Earth rotating, all this happens at a lower frequency. And hence we can do the same averaging procedure, not in space, but in time, and distinguish what we call a gravitational wave. The gravitational wave is the thing that when I average over time, it goes away. And the background is the thing that when I average over time, it stays. And this is really necessary, right? Because so you cannot define even, you cannot even talk about gravitational waves if you don't have some sort of scale separation to distinguish what is background and what is the gravitational wave. So we really need this separation of scales. So well, the condition that we need is that lambda gravitational wave is much smaller than lambda background. And then what we basically do by hand, a bit arbitrarily, is that we introduce some scale in between, right? This we can choose whatever we want as long as it fulfills this condition. The final result should not depend on what we choose here. But we need to be able to define some scale in the middle that we can use to distinguish below this is gravitational wave, above this is background. Okay. So this is what the gravitational wave, what it even means to have a gravitational wave in curved background. Now the question is, now we have a propagating gravitational wave in curved background, and the question is, does that actually contribute to the energy momentum tensor? And why does that matter? Because if it contributes to the energy momentum tensor, right, then recall that Einstein's equation tells you that, well, the energy momentum tensor also sources again the curved background, right? So you wonder, are you going in a loop, right? I mean, you can, on Einstein's equation, you can move things from the left to the right, right? But I mean, at some point you need to decide what are the physical effects. So this is why it's not a completely obvious question if the gravitational wave, which is a perturbation by the metric, can itself curve again a metric at the relevant order in h that we're working at. Okay, so let's see if we can understand what's going on. So to do so, we will take the left-hand side of the full Einstein equation and expand again in powers of h. So expand g mu nu in powers of h. With this picture in mind now. So g mu nu will just be the background g mu nu, whatever it is. And then we will have some contribution to first order in h, some contribution to second order in h, and so on. And now I do this averaging procedure, right? So now I ask these contributions, if I average over d, do they survive, which means they're background, or do they go away, which means they're gravitational wave? Okay, so this guy is just a background by definition, right? So zeroth order in h, let me put a 0. And the typical length scale is LB, right? So large length scales. So small wave numbers if we think of it in Fourier space, small k. Okay, now first order in h, right? Okay, so the typical length scale will be lambda gravitational wave, so small scales. So let me call it large k, right? I mean, basically whatever wave vector we associate with the gravitational wave, which by construction will be much larger than the background. And now comes this turn. This is second order in h. So you have the large k's, the large wave vectors of the gravitational waves, but you have two of them, right? So now you can have the situation that you have k1 plus k2, which each individually can be large, but the entire thing could be close to 0 if they're anti-aligned. Okay, so this is just telling you that if you make the two-point function of something kind of which is dominated by small scales, you will get kind of a large IR contribution, or you will get the IR tail, you will get a contribution to the background. So this has, in this language, if I do a Fourier decomposition of this, it will have small and large k modes. Okay, so if I do this averaging procedure, and if I'm kind of looking for the long length scale modes, right, I will get this contribution, and I will get part of this. And then if I'm looking for the short length scale contribution, I will get this, and again, we'll get the other part of this. So at linear order, everything is completely clear and separated, right? But if I go to higher order, I see that I get mixing of the different contributions. So what we'll do now, because we want to look at to understand this question of the energy momentum tensor, we're going to look here at the large length scale, so the small k part of this expansion, right? So the background and part of this. Okay. If we looked at the other one, right? If we looked at the small length scale, so high k part of the same equation, that would tell us kind of how gravitational waves are sourced by the energy momentum tensor of the matter, right? But that's not the question we want to answer, right? We want to answer how do the gravitational waves contribute to the energy momentum tensor. So for that, we focus on small k part, right? So long length scale. And then, right, I can just rewrite this. So this thing, right, is of course just we have it up here is the 8 pi g over c to the 4 t mu nu, right? So now put that on the other side. So then I get g mu nu background is now I just take the small k part of this second guy. So it's minus g mu nu second order. Let me put just small k. And then plus the energy momentum tensor, the matter energy momentum tensor. And of course, also here I need to, if relevant, take the small k part. Okay, so what is this? So what does it mean taking small k, right? Small k in this language just means taking an average, right? So this just becomes 8 pg c to the 4 t mu nu averaged over some scale. And the same here, right? So I need g mu nu to second order and then averaged over some scale d. And now you see that the What is this equation now telling us, right? Okay, I've just reshuffled some terms, but this equation is telling us that the background metric, right? So the object describing the curvature of space-time at the background level is driven by, okay, the matter energy momentum tensor as we expected, but at second order also by the gravitational wave itself. Okay, so this thing I can simply interpret as just being 8 pi g c to the 4 little t mu nu, right? Where little t mu nu is what I will call the energy momentum tensor of gravitational waves. Okay, so I've identified the object which is made out of gravitational waves and enters the Einstein equation in a way that an energy momentum tensor would, right? It tells us what is the object that describes how the background metric is influenced by the gravitational wave, right? And then more or less by definition, I call this the energy momentum tensor of gravitational waves. Okay, basically via its action on the background metric, right? That's how in GR I identify an energy momentum tensor. So it's nearly a circular argument, but it's not quite a circular argument, right? So I give you a second to think about it and see if there's any questions. This one? Right, so here I'm just expanding in powers of h, right? So these indices here are how many powers of the gravitational wave I have, right? So this guy is just the background, this is linear in h, this is quadratic in h. And now if I have something in quadratic in h, right, it means I have two plane waves that each have a wave vector, k1 and k2. And now I just, have the product of the two. I want to now do a Fourier decomposition of the final result. So I'm asking what is the typical scale of the second term, right? So I have basically h of k1, h of k2, right? So I have some k1, k2, right? And so generically, the resulting vector, which is the sum of the two, right, will be typically, roughly the size of the individual vectors, typically. But I can have the situation that k1 and k2 are just really pretty much anti-aligned. And then my resulting vector, right, which is then just the short part of the triangle, will be very short, right, which means this corresponds to a long scale, right? So I'm basically asking a question, when I go to second order, I go to second order, I average over some length scale, and I ask what is the remaining contribution that is then able to influence the background metric at the scales relevant for the background metric. Yeah. This, you mean the capital T or the small t? I don't think we've had the energy momentum tensor of gravitational waves on the board yet, ever, right? This is the first time. No. This is just coincidence of lack of letters. No. I mean that was just in the metric expansion, right? The tensor component. That little t is basically what we now call h. At least in the TT gauge is what we call h, right? In a proper detector frame, it's not quite what we call h, right? No, that was a dimensionless perturbation of the metric, right? This is an energy momentum tensor, right? So also as units of energy momentum tensor. Right, I'm averaging over some length scale d, right? Which is this scale d, which is defined in a way, can be a length scale or a time scale, and it's defined in a way that it discriminates between the gravitational wave and the background. And it's not unique, right? I mean, here you can, I can make this d a bit smaller and larger, right? It's a bit arbitrary, and the final result should better not depend on the exact value of d. In some way, you're doing effective field theory here, right? You're integrating out, depending, here we're integrating out the short scale modes, right? We're just looking at the long scale modes. And then the scale at which you're integrating out is d. And your results better not be too sensitive to what you chose as the cutoff scale of your theory. Okay. So now we know in principle how to compute the energy momentum tensor of the gravitational waves. So all we need to do is to expand this guy into second order in H. Right? This is the guy that yesterday we expanded to first order in H, right? And it was about 3 blackboards of computations, right? And this is how we got to the linearized Einstein equation, right? So now, in principle, you need to repeat the same game, but go to 1 order more in H, right? And then again, play the game, look for the terms which are symmetric, antisymmetric. Where can I swap around my derivatives? Where can I do partial integration? Where can I do some gauge fixing, right? How can I simplify my result? So we're not going to go through all of it, right? Because otherwise that would take us until Friday. But I'm just going to sketch you briefly how one would do it. So computation, well, G mu nu 2 to second order, and then we're going to make our life a bit easier, right? Because we're going to do directly into T gauge, right? Because I know that the thing that I'm computing at the end of the day is a physical quantity, right? It's an energy momentum tensor. So I can make my life simple and just fix the gauge from the start. So you go through the same exercise as we did last time, right? So you compute the Christoffels, you compute the Riemann tensor, you contract, and you get the R mu nu to second order after some long computation, right? In which you better not lose a single minus sign, because otherwise you get a mess. So you get a term that looks like this: del mu h alpha beta del nu h alpha beta plus 12 terms that I'm not going to write, because all of these 12 terms go away once you impose TT gauge and use integration by parts. Right? And one of the reasons you can use, well, the reason why can I even do integration by parts, right? I can do integration by parts because I have that average over D. Right? The average over D is an integral, and under the integral I can do integration by parts. And so then what you get is that the R mu nu to second order is just this term here, minus 1/4. Lost the minus sign somewhere, probably here. Okay, and this is a TT gauge, right? So we only have IJ indices. And if you contract further, you will find that, so this average is always the average over D, right? You will find that the Ricci scalar is 0. And also the Ricci scalar to first order, which you also need to get the final result, is also 0. And so with that, you can compute the capital G mu nu, right, this guy, right? Because that was just the linear combination of this guy and this guy. And then you plug that back in that expression here, right, to get T mu nu. So then you get that T mu nu is C to the 4 32 pi G del nu H I J T T del nu H I J T T. Mark this with a star, we will need it later. Or usually the part that we're interested in of the energy momentum tensor is just the 0,0 component, right? Because that's just the energy density. So this means that the energy density, so rho gravitational wave, which is the thing that we want to predict, we want to measure. That's just T00, right? And is given by, well, exactly the same thing here, just that now we just, these two things are just time derivatives. So H dot T T I J H dot TTIJ. So this is the result you might have already seen at some point. This is how you, given a gravitational wave, how you compute the energy density, say, in a stochastic background. And there's these averaging brackets in the final result, right? And now you see where these averaging brackets actually came from, right? These averaging brackets came from the need to, in the curved background, define the gravitational waves as opposed to the background. And then they kind of propagated into the expression for the definition of the energy momentum tensor. And from there, they then propagated to the final expression for the gravitational wave. And then, very often, via some hand waving of hands, these averaging brackets turn into ensemble averages, which is kind of okay, right? But it's good that you know where they actually initially came from, these brackets, right? Because when you start off, it's not an ensemble average. When you start off, it's really just a spatial or a time average. Okay, any questions on this? Yeah. Say again? It should mildly depend on D, right? So there's still a D here, right? Because these averaging brackets are an average over D, okay? So it depends a bit on D. But if you think about, if you really have a huge hierarchy here, right? You see, like, if this D is really much smaller than the LB, right? Then averaging over this D will not at all impact this curve, right? But it will completely erase the small fluctuation, right? So you should expect a very mild dependence, but the better is the hierarchy. As the hierarchy kind of goes to infinity, right, the dependence goes to 0. You probably have corrections of order D over L, yeah. Yeah, or then, like, I mean, yeah. Yeah, because here you basically, I mean, here you kind of divided your equation into two parts, right? And then it depends on how clean is that separation, right? I mean, does really the high momentum part, does it leak into the low momentum part or not at all, right? And because in reality, it's a coupled equation, and you kind of decouple the equation based on the hierarchy, but they are still a little bit coupled, right? And that kind of where that residual dependence, well, that's how that residual dependence would go away, right? If you would, because of course the total physics should not depend on D because it's something you put by hand, right? But you made the approximation of decoupling the high K and the low K modes, and that's where the dependence comes from. Any other questions? Okay. So now we're finally ready to talk about how we actually, so now we've understood kind of what gravitational waves are, how they propagate, what the energy momentum tensor is. And so now we still need to discuss how to source them. And once we've discussed how to source them, then we have all the basics to actually talk about cosmological sources. Okay, so imagine you have some object which sources gravitational waves, right? And you have some observer which is at some distance x from the source. And within the source, we measure the position with some y, right? Where y should be much smaller than x, right? So we have, yeah. But we can also, do I want to call it, yeah, no, this is fine. I call it x, and we need y much smaller than x. So we're far away from the source. Then we start with, I just erased it, right? So we start with the equation for the linearized Einstein's equation, 16p j c to the 4 t mu nu, right? And we want to know what is the gravitational wave, like this is the source. We want to know what is the gravitational wave observed here in the far field limit. And that's exact same problem as in electromagnetism, right? Just that instead of the vector potential, you have h bar, right? But exact same problem. And so the solution is exactly the same, right? So as in EM, you get that h bar mu nu at t and x is 4gc to the 4. It will 1 over r, right? It will drop with the inverse of the radius. And then we have an integral d3y over the energy momentum tensor evaluated at the retarded time at position y, and we integrate over y, right? So we integrate over source, and we introduce the retarded time, which accounts for the propagation of the gravitational wave from the source to the observer. Okay, so now we just want to. This is formally correct, right? But not very useful. So we want to evaluate the integral, this d3y integral. And so at the end of the day, here when we go to observe the gravitational wave here, I want to do it in TT gauge. Are there questions? Yeah.
What did we say? 1 over
R.
R.
Right. Well, this is basically R, right? I mean R and X, same thing in this limit. Okay, so I want to be able to describe the gravitational wave here. And here, when I'm far away from the source, I'm in the vacuum, right? So I can choose TT gauge, right? So I want to compute HTT IJ. So at the end of the day, I will only be interested in the IJ, in the spatial components, because at the end of the day, here I can go to the TT gauge. Inside here, I cannot go to the TT gauge, right? Because TT gauge was something I can only do in vacuum. So, but anticipating that at the end of the day, that's what we can do, let us evaluate this integral for the spatial components. So we want to compute d3y tij. And depending on y. And my claim is that this will be given by 1/2 d0 squared d3y yi yj t0 y. Okay? So this is a claim. I will prove it. And then we will see why it is even useful. Okay, so to prove it, I start with energy momentum conservation, right? So we know del mu t mu nu is 0. So from that, I'm basically backwards going to, I mean, this is kind of because I know the answer, right? Because I know the answer, I can kind of try and construct an object that looks very much like this, and then see how it's related to the thing on the left-hand side. So I start by del mu 0 mu, which is 0 with energy momentum tensor. I can write this as del 0 t0 0 plus del k t0 k. I can now act with one more time derivative, so I get del 0 squared t0 0, right? So you see I'm approaching the right-hand side here. This is minus this term here with a, whoops, equal minus del k del 0 t 0 k. Now I can again use energy momentum conservation to flip D's 0 index into a spatial index and change the minus sign. So I get del k del L T L k. Now, yes, I will fit it here. I multiply with yi yj. So I get yi yj del 0 squared t0 0 equal on this side yi yj del k del L T L k. And now I remember that at the end of the day I will be under the integral, so I can do integration by parts, and I can shuffle these spatial derivatives from the t onto the y's. And then, okay, I can do it both ways. I can have this guy acting on this guy, or that guy acting on this guy, right? And of course, the derivative acting on this just gives 1. So I just get, with partial integration, 2tij. And then this is what I wanted to prove, right? Because this is now the right-hand side, and this here is the left-hand side once I bring the factor 2 over. Okay, so this was a necessary step simply to demonstrate this relation here. So with that, we can plug this result back into the expression for h mu nu. So we get h mu nu, well, hij, right? Because we've only done the exercise for the ij components. Right, so this is not yet really the TT gauge, right? This is just taking the ij components of the full expression. Okay, this is just plugging in what we got upstairs. Okay, so what is this telling us? This is telling us that the spatial components of the gravitational wave are sourced by the second time derivative of this object here, which I will give a name. I call it ij evaluated at the retarded time. And this is exactly the tensor moment of the source. Okay, that's how I define a tensor moment. I take the energy momentum tensor and I perform this integral, right? That's the definition of a tensor moment. So what we're seeing here is the gravitational wave, or the spatial components of the gravitational wave, are sourced by the second time derivative of the tensor moment of the source. Sometimes it's also useful to express things in terms of the traceless tensor moment, right? So we can define I/ij as being d3y. The traceless version of this, so we just take yk yl minus 1/3 y squared del kl t0, 0, right? So this is nearly the same thing. It's just that we've made this prefactor here traceless. And this thing also has a name, right? I mean, this is called the quadrupole moment. Right, so sometimes people prefer to use the tensor moment, sometimes people prefer the quadrupole moment. The question is simply if you subtract, it's very similar to what we did yesterday, right? If you want to really subtract out all scalar degrees of freedom or not. And that depends a bit in kind of what exactly you want to compute. So that's just the definition. And now, finally putting everything together, we want to actually go to TT gauge. Right, so we want now to really get something physical. So the gravitational wave in TT gauge. And all we need to do that is basically act with the projector that puts us on the transverse traceless plane, both on the left-hand side and on the right-hand side. On the left-hand side, it's easy, we just put the index, right, and say, okay, now we're talking about the gravitational wave in TT frame. On the right-hand side, we need to explicitly act with the projector, which it does two things. So we need to remove the trace, and we need to make sure that we're transverse. So the way this is usually done, we keep the prefactor. This guy, lambda I j kl, right? This is the TT projector. So this takes whatever 3x3 matrix you give him, depending on the wave vector. I mean, depending on the direction here that you're traveling in, right? It takes whatever you give it with some unit vector, and it projects on the plane transverse to this unit vector. And then here we have the tensor moment, but since anyway this thing will remove all traces, we might as well directly write the traceless version, right? So the quadrupole moment. Okay. I give this a sign so we can refer to it later, right? So this is telling you the gravitational wave in the TT frame evaluated in the far field limit, far away from the source, is okay. It goes as 1 over the distance, not surprising. It has a projector, which is more technicality to get into the T frame, and it depends on the second time derivative of the quadrupole moment. And this is implications, right? I mean, now you, for example, see, I mean, the usual results, right? That type, for example, like a single black hole sitting around in space does not emit gravitational waves, right? Because it doesn't have a quadrupole moment, right? So you need something that has a quadrupole moment, and you need something that has a time-dependent quadrupole moment, right? So a single cylindrically symmetric object does not have a quadrupole moment. Even two black holes, if they're just sitting around and not actually orbiting, they wouldn't have the time dependence, so no gravitational waves. So you need something like a binary black hole system to emit gravitational waves. Okay, maybe that's a good time to take a break. So let's attempt a 10 minutes break, though with one coffee machine. We'll see how that goes. And then see you back in a bit. Yeah. Yes. Okay, so I can notice the symmetry, right? So the number of people drinking coffee is the same, but half the amount of coffee machines, right, means twice the amount of time, right? It's all consistent. Okay. So now we computed the gravitational wave in a far field limit emitted by some source of gravitational waves. Now to connect to what we were doing earlier with the energy momentum tensor, right? I also would like to understand not only what is the amplitude, but also what is the power emitted by gravitational waves. So what is the energy loss to a system from the emission of gravitational waves in all directions? And that goes under the name of Einstein's quadrupole formula. So let's compute the energy of gravitational waves in some volume V. So what I have in mind is I have some volume, right? The source is somewhere well inside this volume. I want this volume to be slightly more circular, otherwise I cannot do the integral. So this is some surface, and there's some unit vector normal to the surface. And I'm interested in the energy inside this volume. So I'm going to do an integral over this volume of T00, so the energy density. And because at the end of the day we want to compute the power, we then take the time derivative. So we're computing the emission of energy, the emission of gravitational waves from some source located inside this volume. And so, okay, we can again use the trick. So we have del 0, T00. We can again use the trick with the conservation of the energy momentum tensor to flip 1, 0 to the spatial index. So we get a minus and del I T0I. And then we can change the volume integral into a surface integral. NI T0I. Oops, 0I. And then we're going to look at this situation where we say, okay, our surface, we just put the surface very far away from the source, and we make the surface spherical, so we can actually perform the integral. So then this just becomes minus r squared d omega, right? I just do the integral over the sphere, t0r. And now I can use the fact that I know that the energy momentum tensor depends only on the retarded time, right? So yes, I can kind of rewrite the derivative in terms of time, in terms of derivative in terms of space. Just wondering if I lost the, did I lose the derivative here? Ah, no, the derivative went into the surface integral. And so I can, under the integral, flip the 0r. So I'm using the fact that the gravitational wave or the energy momentum tensor, right, depends on the retarded time only, and so that I can write dr h essentially is minus del 0 h, right, because h depends on t minus r over c. There's also a 1 over r dependent in h, right? So here, this 1 over r dependence. So flipping the time into a radial component gives corrections of this order, and these I will neglect, and hence this is a tilde. So saying this plus orders in 1 over r squared, which I will neglect, I can flip these indices into the 0, 0 indices and get this expression here. Okay, and now we're ready to write actually the power. So I think I need a new board. Okay, so the power is just that, right? So the emission of energy per unit of time. And now I use the expression which we called star above, right? Which is just the expression, we plug in the expression that we had for t0, 0. The one I just erased, right? So that t0, 0 is given by the average of the time derivative of the gravitational wave squared. So keeping all the prefactors, I get the surface integral from here, and then I plug in the expression for t0, 0, right? So that was h dot ij tt, h dot ij tt. And now I use this expression here and plug in this expression for htt. And I get okay, so I will get the expectation value of lambda times I squared. But this is just a projector, right? So it has kind of properties that, well, if I project on, I mean, it's transverse, it's traceless, right? And if I project on something which is already in the TT plane, right, it does nothing. So I can actually factor out combine the two factors of the projector. So I just get lambda, if I contract it, ijkl, and then in here I get the indices ij, kl. Okay, so the projector is just contracting these indices with these indices. And importantly, this thing depends on the direction that we're emitting in, but this thing does not, right? So this thing does not depend on the omega. So I can take this outside of the integral, and I can perform this integral, which just gives me a series of coefficients and delta functions in these indices. So I can execute the integral. Yeah, I can give you the result, but it's not very insightful, right? It's 2 pi over 15, 11 delta ik delta ij. This can already not be lj minus 4 delta ij delta k l plus del I l delta jk. Okay, but the important part is I can simply perform this integral over the sphere, and then I get the final expression for the power emitted in gravitational waves as Newton's constant, speed of the light to the power 5, and then I get here the quadruple moment contracted with itself with the third derivative. Right, and all the way I keep these averaging brackets, right, which were the averaging brackets that we introduced at the very beginning of the lecture. And this is what people refer to as Einstein's quadruple formula. And now you can, for example, you can take any source, right? You can take, I don't know, an orbiting black hole binary, or you can take a phase transition in cosmology, and if you can compute the quadruple moment, you can directly estimate how much gravitational waves you'll be producing, and also kind of, in the same way, of course, how much energy the system is going to lose by the emission of gravitational waves. Which, for binaries, is particularly important, right? Because for binaries, the first way that gravitational waves were indirectly discovered was by the energy, by kind of the binary not being on a stationary orbit, but like the binary slowly shrinking. And it was slowly shrinking because it was emitting gravitational waves. And the degree to which it's emitting gravitational waves is described by this expression here. Okay, any questions on this? I should maybe mention that throughout, so when we were doing, in particular when we were deriving this, right, but then this of course also enters in what we were doing later, we're using two approximations, right? So, well, three approximations. So one, we're saying, of course, the gravitational wave amplitude is small. Two, we're saying there's a scale separation between the gravitational wave scale and the background scale. And three, we're assuming that the source is non-relativistic. Okay, that kind of entered when we wrote down the expression for h bar up there, right? We're implicitly assuming that the way the source is changing is significantly smaller than the speed of light. So those are the three approximations that went into this derivation. I think there was a question here. No? Okay. This thing here. Okay, so what happened here? Oops. Okay, so I'm using, right, that the T0R, right, is del 0 Hij del R Ij, right? Okay, and now I'm using this, right? So I'm using that Hij depends on some function of the retarded time divided by the radius. Okay, so that means that if I'm taking dr Hij, that's the same thing as minus del 0 Hij, right? Because I'm just I'm doing chain rule, right? F prime and then the derivative inside, plus corrections of 1 over r squared, right? Which is when I'm acting with the derivative on the r. Okay, and now I'm just plugging this relation inside here, right? So you see that basically the 0r component the leading order in 1 over r is the same as minus the 0, 0 component. Yeah, but thanks for asking. I think I was not super clear when I explained this. Okay, any other questions? Okay, so let's do a quick example. Yeah. A quick example of how that looks like concretely. Okay, and the example will be the thing that we've actually observed, right, which is a binary system. So we have 2 black holes, and they're orbiting, and they have mass m1 and m2. They have some distance between them, r. Yeah, I think that's all that we need. But I also want coordinate systems, right? So I'm going to put x and y. Okay, so they are orbiting in the xy plane. So that's okay. That's kind of Newton mechanics, theoretical physics 1 problem. So we know, right, that we can reduce this to an effective 1 parameter problem by separating the motion of the center of mass and the relative motion, right? So we know we can introduce the reduced mass, mu, m1, m2, m1 plus m2. We will, for convenience, also introduce, okay, we also need the total mass, right, m1 plus m2. And because that's the object that will appear later, we will also introduce what is called the chirp mass, which is mu to the power 3, m to the power square to the power 1/5. That you don't usually introduce when you do this in theoretical physics 1, right? But it's the parameter combination that will appear at the end. And then we know from Kepler's law, we know that the orbiting velocity of the system is given by g m divided by r cubed. Okay, so now we want to compute the gravitational wave emission, right? By this formula here. Okay, so what we need is the second derivative of the quadrupole moment. So what is the quadrupole moment, right? To compute the quadrupole moment, we first need to understand what is the motion of the, basically we need to solve the system, but we know how to solve the system, right? I mean, basically we have everything here, right? So we know for the reduced system in the coordinates of the relative distance and the reduced mass, x as a function of t will just be r cos omega st, and y is just r sinus omega st, right? So I've dropped the phase because it doesn't matter. And now we can directly compute the quadrupole moment, right? So we compute Ixx, right, which was just the integral, volume integral over R1, R2 times the energy momentum tensor. Now, the energy momentum tensor is just a delta function at the position of the 2 particles, okay, or at the position of the reduced position of the effective 1 body problem. So this is very simple, right? This is just going to be mu r squared cos squared omega st. All right, so it's simply the x component squared times the energy momentum, which is just the reduced mass. And of course, the same for y, right? So then you just get the sine squared, and for the xy, I will get cosine times sine. So then I can compute the gravitational wave observed sometime t And I'm going to make my life easier, and I'm going to just put the observer on the z-axis here so that I see the binary face on. But that's just because I don't want to mess around with projections, right? And so we use the formula there, right? So we need the sum. And also, like, since now I'm putting myself on the z-axis, I can forget about the projector, right? Because I'm just like directly looking at that thing face on, and I don't have to worry about it. So all I need to do is really just take the second derivative of this plus the second derivative with yy. I already see that the cosine square plus the sine square will just give 1. And so if I plug in, well, just this prefactor and the prefactor up there, I will get 2g 5c squared 4 mu r squared omega s cubed square. Right, the square comes because we have, no, wait, it's because I was already computing the power. Sorry, my bad, I was one step ahead. Okay, so sorry, I was yes, sorry, we want to, let me take one step back. We have this expression, and we actually want to rewrite this cosine square just using a trigonometric identity as 1 plus cosine 2 omega st. Okay, that was actually an important step, because that tells us that the gravitational wave now, when we just use this formula, so forget what I just said about the cosine squared plus the sine squared, right? I was jumping ahead of myself. This is the quadrupole moment. The gravitational wave is just proportional to the second derivative of the quadrupole moment, which means we will get something where this one just drops out, no time dependence, and we will get something that oscillates at twice the frequency of the system. Okay, so the system is orbiting at the frequency, and the gravitational wave will always have twice the frequency of the system. And that has something to do with the fact that the gravitational wave is spin 2. You basically need 2 orbits of your system in order to get kind of the same configuration for the gravitational wave. But now to put back all these factors, what you get here is mc to the 5/3, omega s to the 2/3, cosine 2 omega st. Okay, so this cosine is just this cosine, and these combinations, right, is just kind of a complicated way of writing that prefactor combined with this prefactor. And I'm writing it in a way because these are kind of the physical parameters that we will, this will give us the physical parameters that we can observe about the system by making the gravitational wave observation. Where here, this r, right, this r is, it's not this r, sorry for the notation, right? I mean, this r here is the distance between the two binaries, and this r is the r that is appearing up there. So it's a distance from the observer to the binary. So maybe I should, let me call this z, ez, right? And then this will be z. Then we maybe don't have this confusion. Okay, and now, so this is just to give you an example, right? How, I mean, these formulas with the quadrupole moment are a bit abstract, right? But then when you do the actual computation, I mean, if the system is simple, right, then the computation is extremely simple, right? And you can immediately read off the properties that you want to read off. So here in particular, we can immediately see that the gravitational wave has a frequency of twice of the system. And we can also immediately see that the amplitude scales with the frequency, right? So as the binary loses energy, right, as the black holes go closer together, the Kepler frequency goes up, and hence the amplitude goes up, right? Which is exactly the chirp that we observe in the LIGO system. Okay, and then we can play the same game to compute the power, right? So now we have the gravitational wave, we can now compute the power. So it's that expression over there. Well, I don't have to write it again, right? But so I take that expression for the power. I plug in my energy, my quadrupole moment. I take 3 time derivatives. And now I have to square it, right? And this is what I was already jumping ahead, right? So now I take the cosine and I have to square it accordingly. And now what I will get is 2g 5c squared 4 mu r squared omega s 3 cubed. Square. I mean, this is just from the square of the II. And then I get the cosine squared plus sine squared, right? So that's just 1. And that means that everything together, I get some prefactor which depends on the chirp mass, mc, and depends on the frequency. Right, so the heavier my system and the closer the black holes are together, the more energy loss I'm getting. And then the final thing that we can compute is essentially the waveform. Because so far what we've done is slightly inconsistent, right? Because the Kepler frequency, I mean, what I wrote down here for the Kepler frequency, that's just a Newtonian problem, right? In the Newtonian problem, there's, however, no energy loss, right? The Newtonian problem, you would just stay forever on the same orbit, right? But now I've used the Newtonian ansatz to compute the gravitational wave, and it compute the energy that I'm emitting with the gravitational waves. But that's, of course, inconsistent to what I did at the very beginning, where I said the orbit was constant. Now, the reason this is still okay is that the timescales are very different, right? The black holes are orbiting pretty fast, right? And the energy loss in gravitational waves is pretty slow. So I can kind of do an adiabatic approximation where I say, okay, at any given point in time, I can use this estimate to compute the gravitational wave and to compute the power emitted in gravitational waves. But now I need to go back and I need to say, okay, how does the distance between the black holes and correspondingly the frequency change in time? So to estimate that, so the shrinking orbit, to estimate that, we take the total energy of the orbit, again, just in the Newtonian approximation, which is G m1 m2 divided by 2r, which I'm just going to rewrite in terms of the units that we're using here, right? Because I want to use the omega s and I want to use the mc. So that is equivalent to saying 1/2 g to the 2/3 omega to the 2/3 mc to the 5/3. We call this 2 star. And now I can do dE over dt, which on the one hand is just given by this expression here, right? So minus 32, because now this is the power emitted, right? This is the power lost, so there's a minus sign. But this is, of course, now has to also be equal to simply taking the time derivative of this, right? And when I take the time derivative of this, I mean, the Newton's constant is not going to change. The mass of the black holes is not going to change, but what is going to change is the frequency. Okay, so this is also has to be according to this equation here. minus 1 over 3 g to the 2/3 omega, mc to the 5/3, and then omega s to the minus 1/3 d omega s over dt. And now we have a differential equation for omega s, for the frequency of the system, right? We have basically, forget about the left-hand side here, right? And view this here as simply a differential equation for the frequency, which we can solve. Right? It's a simple differential equation. Do we need to? Okay, yes, we can do it. Right? So if we put everything okay, so we have omega s to the 10/3, right? And then here we have minus 1/3. Yes, so we get that omega dot, right, which is, should be okay. Omega dot is proportional to omega to the 11/3, right? Which then means that the gravitational wave frequency, which is just 2 pi times 2 times this, right? So gravitational wave frequency proportional to this, right? So we'll have the same relation. And okay, there's some constants here, right, which are just the constants of this equation. But the point is, this is something you can easily solve, right? And what you will get is that the gravitational wave frequency scales as tau, which is the time, right? But it's a time to coalescence. That's the way it's usually parameterized, to the power minus 3 over 8, right? Which is just coming from this relation here. And this thing here is exactly kind of the smoking gun chirp signal that you would see in LIGO, right? Because in LIGO you see how the frequencies, how the amplitude kind of goes up as the frequency goes up of the signal. And there's some prefactors here, but it doesn't change this proportionality, right? So whatever merger you observe, if it really is a mergery of any compact binaries, which I can describe as pointite objects, I should always be able to see this relation between frequency and time, on top of kind of that I expect an oscillating signal. So I expect an oscillating signal with an amplitude, with a frequency that change in exactly this way. And then kind of you can convince yourself that what you're actually seeing is really, it's one of the ways you can convince yourself that what you're seeing is a gravitational wave and not something else. Yes, I think that's basically all I wanted to do, right? I mean, now that you have the concrete waveforms, right? You can play all sorts of games, right? You can look at this off axis. You can look at how much energy loss you have in a certain amount of time. You can also see how much energy loss do you have overall into gravitational waves compared to the total energy in the system. And we'll find that typically you lose usually about 10% of the total energy of the system goes into gravitational waves over the course of the in-spiral. And that most of that typically happens towards the end. One word of caution is, as I said, we assumed early on that the velocity of the system is smaller than the speed of light, right? So this is all fine as long as the black holes don't go too close together, right? In the very last stage of the merger, all our approximations break down, right? Because then the speed of the black holes becomes close to the speed of light. The gravitational waves emitted at least close to the source, right, which would have order 1 amplitude. And also the scale of the gravitational waves then becomes comparable kind of to the scale of the background. So everything breaks down, right? And then if you want to really describe that very last bit of the gravitational waveform, you need more complicated methods. But as long as you kind of stay a few oscillations away from the final merger, these approximations are excellent and they capture all the relevant physics. Okay, so that's going to be more or less, I think, the last time that we talk about astrophysical sources, right? Because really we want to be talking about early universe sources, but I just wanted to give you that as an example of how these rather abstract formulas about computing the gravitational wave from any source, from an energy, from a tensor moment, how they actually work out in practice. Okay, are there any more questions? Yeah. Sorry, say it again. Yes. Okay, you would need to some extent, you would need to put the prefactors back in, right? That I dropped here. But you can, I mean, okay, the typical time scale. Yes, I mean you can. Okay, so the typical time scale here is really just the frequency of the orbit, right? So the directly omega s is the time scale here, and so you would need to compare the time scale of the motion with this change in time scale here, right? And so now, since I didn't give you the prefactors, right, you cannot do it, right? But if you go back to, now it's gone here, to this equation, and you evaluate the relevant prefactors, right, you should find a number which is much smaller than unity compared to the actual frequency evolution. No, I think it's always a good approximation. The prefactors, exactly. So there is a prefactor. Okay, there is an MC dependence. Well, I mean, okay, so the frequency and the mass are not independent quantities, right? Because this is, I think, because the frequency is related to the mass via the Keplerian law, right? So it's true, right, that yes, this prefactor will depend on, I mean, let's maybe make our life simple, right, and just take two equal mass black holes, right? Because then MC just becomes M, right? And there's just one mass scale in the problem, right? And then it is true, yes, there's a, I mean, not sure we can do it on the fly, right? But basically what this thing here, if we put in the powers of M in the equal mass limit, it should be something like this. 5/3 F11/3, right? And now you need to take into account here that omega also depends on M, right? And now you need to compare omega with d omega over dt, but taking into account that relation. Right, so you cannot go, like once you fix the mass of the system, you fix the frequency. Okay, so you cannot vary mass and frequency independently. So the mass is constant, right? Yes, and the only way the orbit changes is by the frequency change. No, but the mass doesn't change. But it also depends on radius. The mass doesn't change, right? You fix the mass, right? You fix the mass. You have two black holes, right? They are what they are, right? 2 point-like particles, right? And then as they evolve with a certain frequency depending on how close they are together, right? And now you lose energy, and by losing energy, you move closer together and you speed up. Okay, so that's how they're related. And like on the fly, I can't tell you where there's some number here which is much smaller than order 1, right? And you should get it when you plug in all the prefactors, right? But just think about it, right? I mean, LIGO, right, observes gravitational waves, right, at 100 hertz, right? These black holes, you know, are, I mean, you know, they can be orbiting for years, right, before they finally merge, right? And even then, when LIGO sees them, right, then LIGO sees the last second, millisecond, 10 seconds, 1 minute, right? That's just much, much longer than the inverse of the frequency. So it breaks down. Here you can see where it breaks down, right? I mean, it breaks down in basically the time period, which corresponds to, like, if you observe a merger at 100 hertz, right? Then basically it breaks down in the last 1/100 second of before the merger, right? That's basically what this is saying. That's just a frequent. That's basically this. This, so FGW is 2 omega s, and then there's just the 2 pi. And I hope I put the 2 pi on the right place. Yes, 2 pi f is omega. Okay, so it's just the frequency that we read off here, and then it's just angular frequency versus frequency in units of hertz. So I think it should. It should, in the sense that you lose energy, right? So you can think of it in some sense. You can think of it as in some sense you can think of it as a Newtonian problem, but with a friction component, right? So you will always kind of, to minimize the energy, I think you will always move towards the circular orbit. But I mean, it's true that we've made. I mean, here when I set up the problem, right? I mean, we made some simplifying assumptions, right? So A, we assumed that it was perfectly circular, and B, we assumed that we're seeing the thing face on, right? In reality, you can have some ellipticity, at least initially, right? I mean, as you say, right, over time it will anyway go away. But also, I mean, as soon as you kind of observe it off axis, or we set the spins of the black hole to 0, right? Because we just said, okay, these are point-like particles, right? I mean, if you add the spin of the particle, if this is not a black hole but a neutron star, it has some size, right? Some deformability, right? All this modifies this wave function, but it doesn't modify dramatically, right? I mean, it typically gives you some. You always get this part, right? Because that's just telling you the time dependence of the system, and then you will get kind of some slightly modified prefactor. I mean, so I think you need to basically. I mean, the same analysis. I don't know, right? Because here we basically, I wrote the solution, right? I mean, I think what you need to do is you need to kind of, with the friction. So here we can compute. You can do the same type of analysis, right? Because you can basically you can write down, you can start Newtonian, right? But with elliptical initial conditions. You can compute the energy loss, right? That is completely generic, right? I mean, this expression assumes circular orbit, right? But the expression that we had beforehand, right, which is now gone, right? That did not assume circular orbit, right? So you can start general, you can compute the energy loss, and then you can, in your Newtonian problem, introduce the energy loss, right, and find the solutions to your system in the Newtonian problem. And then you can plug that back in here, right, and get your final result. Okay, any more questions? Okay, I think good enough.